我下面介绍一下他的一些简历，下面那个海报上面也有，这里再重复一下1-2分钟时间啊。他的 barriers 他是1979年写的这个矿物加工的著作 Mineral Process Technology， 他这个书的话是我们至少是中亚大学这个双语教材，它现在已经第8版了，我们当时用的可能第5、6版的样子，现在第8版了。然后他是1988年创办，一直担任主编的 Mineral Engineering 期刊，是我们这个矿物加工领域最权威的学术期刊，也是中科院1区的 Top 期刊，也是17年刚刚入选的 Top 期刊。这也是非常难得的，因为 Top 期刊一般影响因子啊或者那个什么都很高，但是我们这个 Mineral Engineering 就是能成为中科院的1区 Top 期刊是很难的。他1991年他创办了 MEI Conference 系列，就是特别是里边的这个 comminution， 就是碎膜，还有这个flotation， 它这2个会议的话非常有影响力。每2年举办一次，但每次的会议参会人数大概都是300-400人，然后都是来自40-50个国家。我去年有幸参加了一次那个 flotation 会议。1999年，他创办了这个 Mineral Engineering International 这个网站，他就是分享一些我们矿物加工领域的一些最新的研究成果啊，或者说一些最新的发表的一些论文啊，他觉得是亮点论文，还有一些发表一些就是说，他这种就是一些求职的广告啊 ，post doc 啊，就是说post 就是那种还有 PhD 啊这种职位的这种信息，他都发表。所以说这个大家就是有兴趣的话，可以关注一下 MEI 这个 online 这个网站。威尔士他是英国利兹大学的校友，在50年的矿物加工生涯中，一直致力于促进矿物加工知识在世界各地的传播和普及，为国际矿物加工学科的发展做出了杰出的贡献。2014年获得了国际矿物加工理事会的杰出贡献奖 （Distinguished Service Award of IMPC）。2017年获得了国际材料矿业协会杰出贡献奖，Battle for Excellence 这个奖，这2个奖都非常有分量。然后的话，我们也打算聘他为我们学校的名誉教授。具体时间的话，因为还有一些突发的事情发生，我本来是定在后天上午9点钟，可能具体时间我会具体跟大家及时的沟通，告诉大家。不好意思，郑老师，我因为时间到了，我就开始了啊。Now welcome Dr. Parables to give his presentation.
Thank you. Thank you very much, Zheong. I hope he was saying nice things about me. Didn't understand a word, but thanks anyway. I'm going to be basing this lecture. First of all, before I start, I feel very honoured to be part of CSU. I was here last year, so this is my second visit to Changsha. I feel very honoured by it, and I'd like to thank particularly Zheong, who invited me, and he's done all the organisation. He's a great man. Treasure him. The talk I'm going to give today is on the importance of, and the evolution of, and the future of mineral processing. I'm going to keep it very, very basic because I'm not a researcher. I'm more a communicator and a journalist. So all I'm going to do is give a general overview. I'll be basically aiming this at the young people who are just starting their careers in mineral processing. I want them really to understand how important mineral processing is and what the future might be. You probably know much more about the future than I do because you're researching, so what you're doing now is going to be the future. But I'll give you my general ideas about this as well. What I'll start off with is nothing. What I'll start off with is this. Okay, can you? Yeah. This table here, I did a survey recently of young people who are just about to go into universities to study science. So these were sixth formers in the UK, young people about 17 years old, and I asked them all one very simple question. What do you think is the most important technology in the world, science technology? What's the most important industry or the most important research area? The most important technology, anything you can name which is to do with science. What do you think is the most important? They came up with all different things, but these were the top 10. Don't bother writing them down, it's just for your information, but these are the top 10 which came out. And they're all very, very important, obviously. Medical research, high-tech industries, agriculture, very, very important indeed. I asked them then, what have all these industries got in common? And they didn't know. And what all these industries have in common, and you can name many, many more of them, probably the top 100, they've all got one thing in common. They all depend totally on the mining industry. Without the mining industry, none of these industries could perform. The mining industry is the great feeder. It feeds everything. It's the primary industry. You've probably heard it before, but everything that we touch, everything that we use is either mined or it's grown. It's very, very important indeed. All civilizations, all great civilizations had or have a great mining industry. It's very, very important indeed. You look at the various ages of man, the Stone Age, the Bronze Age, the Iron Age, they're all dependent on what we take from the ground. So it's incredibly important. And they didn't realize that. And when I pointed that out to them, they said, no, it can't be. The mining industry can't be that important. The mining industry is a dirty industry. It's used by capitalists just to make money. It bespoils the environment. It's not a great industry, but we know better, it is. And never forget it. The mining industry is the #1 industry. It feeds everything. So, where does mineral processing fit into this industry? That's what I want to talk about first. How important is mineral processing? Mining is crucial. How important is mineral processing? Well, to really look at how important it is, we have to go back in time. And I'm going to go back in time to roughly 300 years ago. 300 years ago was the dawn of what we in the West, I don't know if you call it the same in China, but we call it in the West the Industrial Revolution. You call it that? Yeah. So it's the Industrial Revolution where machines started to take over from humans and production started to escalate. And that took place at the beginning of the 18th century. Prior to the Industrial Revolution, mining was fairly simple. The deposits which were being worked were all fairly high grade. You know, the miners could just choose whatever they liked. They're all high grade. Very, very little mineral processing was required. If you think of mineral processing, the only mineral processing which took place really was hand sorting. So they'd have teams of people just sorting out waste rock from valuable rock just by hand. And they could do this because the ores were very, very high grade indeed. And there wasn't a great demand for metals at the beginning of the 18th century. The mines which were being worked were all fairly shallow. They couldn't go very deep. And the reason they couldn't go deep was because the great enemy of all miners is water. As soon as you start to go deep, then you encounter water. And that water has to be pumped out of the mine. And that's expensive, or in terms of early 18th century, it was almost impossible to go deep and pump out lots of water. They didn't have the equipment. So what they used to do is, if the mine was on a hillside or fairly high up, they'd dig out a very long horizontal shaft, which you can see here. It's called an adit. So that adit would drain the mine. So any water which accumulated down at the working level would just drain out. And that was very, very important. But it could only go down as far as the nearest river or the sea. So you were limited in terms of the depth of mining which could take place. This is an adit in Cornwall. I'm standing by this adit which is still pouring out water from the cliffs. And that's water from a mine which actually shut down 150 years ago. And it's still draining through its old adit. So the adits were useful, but you couldn't go below the adit, or not very far below the adit, because you had no way of pumping. Why did the Industrial Revolution take place? It took place because of one of the most important inventions ever. And that invention was the steam engine. I can't stress enough how important the steam engine was. The steam engine allowed machines to start to take over from humans, production increased, and because production increased, there was a need now for more metals. And the most important mining area in the world was down in Cornwall in UK, and what they developed here was the pumping engine. I'm sorry the animation's a bit quick, but basically the pumping engine uses steam to pump water from deep in the mine. And that revolutionized mining. It revolutionized mining all around the world. It allowed mines to go deeper and deeper and deeper. And where I live in Cornwall in UK is regarded as being the birthplace of modern deep level mining. This is where deep level mining started. Most of the copper, most of the tin came from this area of Cornwall in the 18th and the 19th centuries. And this is a typical Cornish engine house, which houses the pump, which pumps the water from underground. The pump wouldn't pump all the way to the surface in most cases, it would pump to the adit. So it would pump up to the adit and then it would flow out. So this is the map of the UK. Don't know how familiar you are with this, but the UK is essentially 4 different old countries, now all amalgamated into the United Kingdom. You have the red is England, the green is Wales, the blue is Scotland, and the light green up there is Northern Ireland. Down below there is the Republic of Ireland, which is very much part of the EU. You've probably heard about all the controversy about the Irish border. It's because Northern Ireland is part of UK, but Southern Ireland is, or will be, just part of the EU. Down here, right down in the far tip of England, is Cornwall. So this is exploded here. And this is where basically all the metal mining took place in the 18th and 19th centuries. It was the biggest producer in the world of copper. It was the biggest producer in the world of tin. And where these deposits occur are on these areas here, the red areas, which are granite. This is carboniferous granite. And where the granite occurs, you get copper and you get tin. You get copper closer to the surface, you get tin below the copper. So a lot of the mines in Cornwall actually started their life as copper mines, and then when the copper was depleted, they became tin mines because they went deeper and deeper. Where I live, where MEI is just around here in Falmouth, so it's part of Cornwall. And this is the legacy of all those mines. These old engine houses on the cliffs, studied all the way around Cornwall. And they've got this impression of being romantic. You know, this is where the tourists like to see these things. Artists, photographers, all come to Cornwall to take pictures and paint these old engine houses. Beautiful. But the reality wasn't. If you were a miner in the old days, mining was pretty awful. The mines eventually went down to about 1,000 metres, which in the 18th and 19th century was very, very deep indeed. And the conditions were really arduous. The temperature was over 40 degrees centigrade, very, very high humidity, so the miners would sweat a lot. The conditions were appalling. There was hardly any air. The only light they had was from candles on the head. And there were many, many rock falls, so it was very, very dangerous indeed. Then at the end of the shift, the only way the miners could get back to the surface, the only way they could get down to the mine was by ladders. There were no hoists, so they'd have to climb 1,000 metres of ladders at the end of a long shift. And it could take them 2 hours to get down to the mine, to the working area. It would take them over 2 hours at the end of the shift to come up to the surface. And you can imagine it, can't you? They come up to the surface drenched in sweat from toiling down in the bowels of the earth, come up to the surface where maybe it was winter, there's a howling gale, it was raining, they'd have to walk to their dwelling. Not impossible to believe that the miners very rarely passed 40 years of age. That was roughly the lifespan of a miner. So initially it was copper which was worked, and in the mid-19th century, Camborne was the biggest producer of copper. It produced the whole world produced about 60,000 tons of copper, which is not a lot compared with today. You know, today you're talking about well over 20 million tons of copper per year. But Camborne was the biggest producer of copper. And it was also the biggest producer of tin. The tin ores had to be ground, and there were no proper crushers, there were no ball mills, there were no rod mills. Grinding took place in stamp mills. Now, if you're involved with comminution, you should know what a stamp mill is. It's just basically big anvils which crash down on the rock with no control whatsoever, produce a lot of very, very fine material, and this was all they had. And these were also driven by steam, by engine houses. The copper ores needed very, very little upgrading. What's the rough copper grade now in the world? Anyone tell me? You know, if you look at the mines in America and South America, what would you say was an average grade of copper? It's probably less than 0.6% copper. But the mines which were being worked then contained around about 14% copper. Huge amount. They could be dug out, they could be very, very easily concentrated, I say concentrated, mineral processing. They used teams of women, and the women just sorted out the waste rock from the chalcopyrite. Very, very, and that could then be directly smelted. So there's no mineral processing needed. The tin ores are a little bit different. They had to be ground using these stamp mills. And then they were concentrated by very, very, very crude gravity concentration processes. Cassiterite's got a density of about 7. The waste minerals have a density of about 2.7. And these were some of the old mines which were being worked in the 19th century. What were the gravity concentration devices like? How many of you are involved with gravity concentration? Researching gravity? Some of you are. Okay, no hands. You know the modern gravity devices, but these were the devices which were used in the 19th century. These were used everywhere. They're called buddles. You'll never see them now, but if you're involved in mineral processing, you should know a bit about the history, and these are buddles. Basically, a buddle is a static device. So the ore was sent onto these buddles, and the heavy minerals would flow down that convex slope slower than the light minerals. So the light minerals will be taken off at the bottom. The only moving part was a brush, which brushed off the minerals. And periodically, every few days or maybe every few weeks, the buddles were stopped, no flow to the buddles, and they were dug out. And that was concentration. That was it. That was the only method they had. So mineral processing in the late or the middle 19th century, there were only 2 methods available. Hand sorting, very, very crude. Buddles, very, very crude. Nothing else. Luckily, the tin ores had very heavy minerals and light minerals, so they could be separated by gravity. There was one big problem. I talked to somebody today about arsenic in the ores, arsenic and how to get rid of arsenic. The tin ores contained a lot of arsenopyrite. Now, arsenopyrite is also a very dense mineral. It's got a density of about 7. So it couldn't be separated from the cassiterite. And it had to be, because if the cassiterite went to the smelter to produce tin and it contained arsenic, it would produce a very brittle tin which had no value whatsoever. So the arsenic had to be removed. Arsenopyrite. How would you remove it now? Hands up. Come on, don't be shy. Someone tell me how you would remove the arsenyl pyrite now. Okay, I'll come back to it. It's a sulfide mineral. You'd use flotation now, okay? But there was no flotation, all right? So how did they remove the arsenyl pyrite? They did it in what's called calciners. They heated the concentrate up to a very high temperature and put air through the system, and that blew off, oxidized the arsenopyrite into an arsenic trioxide. Sulfur dioxide went into the atmosphere, polluted the atmosphere, but nobody cared about that. And then periodically, men were sent into these labyrinths where the arsenic trioxide was condensed out, and they would dig out the arsenic trioxide. Arsenic trioxide is very, very highly poisonous. You only need to ingest a little bit or get it on your arm or on your skin, and you may be dead. So this is one of the most dangerous jobs in mining. It's probably as dangerous as working underground. But they did have protection. Protection they had was 2 pieces of cotton wool up the nose, a handkerchief around the face, and a bit of oil on their arms, and that was it. So really there wasn't any protection at all. So that was concentration, that was mineral processing in the mid-19th century. Now, no one worried about it. There were no mineral processors. There was no discipline, no professional discipline called mineral processing at that time. All the mineral processing was taking place by the miners. So, you know, just very, very crude. Nobody had researched it. They didn't need to do. But by the end of the 19th century, they encountered a very, very big problem. If we look at the copper ores, I said the copper ores contained about 14% copper, and the worldwide production of copper was about 60,000 tonnes per year. Now, by the end of the 19th century, that had gone up tenfold. Well over 500,000 tonnes of copper was required by the end of the 19th century. Why is that? They're all asleep. Why do you think that is? Why was there such a big demand for copper towards the end of the 19th century? It was the introduction of electricity. So electricity was now invented. People could power, rather than using steam, they could use electricity. Electricity was used for lighting, for everything. And what do you need for electricity? You need copper. You need copper wiring. So the demand for copper soared. Big problem now, because all the high-grade ores which were being mined soon got completely depleted. So the Cornish mines closed. You couldn't treat them. The only copper which was available, and it was available in very, very high quantities, was in North and South America, big deposits. Big problem though, it was very low grade, probably less than 1%. It was all sort of very finely disseminated. So it couldn't be treated. You only had gravity concentration, you only had sorting, hand sorting. So there's no way to treat these ores. And this applied to virtually every base metal, zinc, lead, all the same. They're all required for this new industry which was developing. And all the high-grade deposits went. We had low-grade deposits which we couldn't treat. So the mining industry was in a crisis. Ordinary people wouldn't have known, but the mining industry was basically dead. It was dying. It had to be revived because you need the mining industry, you need metals. And there was nothing to treat these ores. Now brings me to the point of how important mineral processing is. Because this was the first time that mineral processing was intensively researched. The end of the 19th century, the beginning of the 20th century, people had to research. They looked for a new method of concentration, one which could deal with these low-grade, finely disseminated ores which were around the world. And the process they found was froth flotation. So they did intensive research, and flotation became the dominant process. Flotation could be used. It could be used to treat fine ores. It could be used to treat very low-grade ores. It took a lot of research, but it was patented in the early 20th century. Then after that, it took off in a big way. By 1930s, everyone was using flotation. It's used everywhere. The development, initially it wasn't very selective. You know, you just blew bubbles through the slurry and the minerals floated. But you couldn't selectively float them. But by 1930s, xanthates had been developed, collectors, depressants, activators, they'd all been developed. So now you could start to actually concentrate and separate these minerals from each other. It's profound. It's probably the most important invention ever since the discovery of smelting. If you're involved with flotation, I know many of you are, be very, very proud because it really is. I always call it the most important invention ever. I wasn't around when smelting was developed, but smelting was developed about 3,000 years ago, and that was very important, obviously. But flotation, just as important. It's the most important technique. It's probably the most important technology we have in the world, because without flotation, think about it. Without flotation, how would you treat copper ores? Copper ores would be precious metals. Be very, very difficult to treat. You could use direct leaching and so on. You could use bio-leaching, but very, very expensive. You have to concentrate them. So flotation, very, very important indeed. Can't stress that enough. Bear that in mind. So once you develop flotation, what it also developed is a new discipline, the mineral processor. The mineral processor then became a professional person for the first time. Not divorced from, but part of the mining industry, but a separate profession. And that was important. So how did it develop after flotation? The evolution of mineral processing. Well, the first thing, we had to get rid of those stamp mills. Stamp mills were useless when you're talking about very fine particles and flotation. Flotation needs particles of a very small bandwidth. You can't just treat a whole batch of particles different sizes. So you had to have some control on the grinding process. Stamp mills didn't give you that control. Ball mills did, because with a ball mill, you could run them in closed circuit with classifiers. And if you run them in closed circuit with classifiers, you can actually control the particle size. So that was the next fundamental step, comminution. And then after that, we had things like crushers, but look at that. That's a crusher in 1935, a cone crusher, and that's a crusher in 2012. Are they any difference? So very, very little evolution of things like crushers. And there was very, very little evolution, actually, of anything after the discovery of flotation and after the discovery of ball mills and classifiers. Throughout the 20th century, very, very little happened. We were just content. These things work. Wonderful. Let's use them. And this is a typical grinding circuit in the 1970s in Zambia. And this was typical of a grinding circuit in the 1970s, in that you had whole banks of very small mills running in parallel, each with its own classifier. These are all running in closed circuit with rake classifiers. Many, many of them. And that was exactly the same as in the 1930s. Someone came back from the 1930s, went to a mine in the 1970s, they see virtually no difference. That's the way grinding was done. That's the way grinding had always been done, and that's the way it was being done. Flotation, very similar. This is a defunct flotation plant in Zambia, but it shows what flotation was like. Lots of tiny cells, all running in series and in banks of cells. So many, many small cells. And this was also typical of what flotation was like in the 1930s. So between the 1930s and the end of the 1970s, there was very, very little development. You know, things worked, ore grades were still fairly high. There wasn't really any need to do things more efficiently. Big change came in the 1980s. Column flotation came in. Column flotation was going to be the answer to everything. You wouldn't need mechanical flotation cells again. Everything would be done by column flotation cells. Well, it didn't work like that at all. Column flotation cells are still being used, but they're basically used as cleaning operations in most cases. Roughing operations are still carried out by mechanically agitated cells. So column flotation promised a lot, but didn't really deliver that much. They're still used, obviously. Big development. The big development in the 1980s was computers. Now this is a computer operation in the 1960s when I was at university. And I can remember these computers. That computer has probably got 100th of the computing power of your mobile phone. Virtually nothing. Big banks of computers, everything stored on magnetic tape. There was a survey in Britain in the 1960s when I was at university, and the government survey said there could never possibly be more than 6 computers in the UK, ever, because they're so difficult to run and they needed cooling and everything. But we know what happened. Personal computers came in and so on. How did that affect the mining industry? Well, it affected every industry. The way it affected the mining industry was now there was a trend. You could actually design big cells. Those small cells I talked about started to disappear. You don't see them now at all. The reason they disappeared is because the computer could be now used for design, and also if you use big cells, you've got smaller capital costs, you've got smaller operating costs. But the other big thing about very, very large cells indeed, this is the biggest cell in the world, by the way. Well, it's probably not true. There might be big ones in China, but this is the biggest one in the Western world. The other big thing about cells like this is that if you've got a big cell, they're easier to instrument, to put instrumentation in for process control. And the computer allowed process control. So process control came in a very, very big way. And if you imagine those small ball mills and those small flotation cells, if you try to instrument all those and control them, you would never do it. It's virtually impossible. But with very, very big cells, you can do that. So process control, computers brought in very, very big cells such as this, did the same for grinding mills. This is the biggest semi-autogenous grinding mill in the world, 12.8 meters in diameter. And very, very big mills are now taking over these long banks of small ball mills. So you don't see those anymore. You see very, very big mills in operation. Oops. So what other developments took place? Most of the developments actually from the 1980s onwards took place in comminution rather than flotation. And one of the big developments was the high pressure grinding mills here. Basically it's a roll crusher, and roll crushers have been used for a very long time, but it uses very high pressures to grind the ore, and it improves liberation, energy consumption is less. So high pressure grinding mills in the last 20 years have started to become used more and more. Another thing which is being used more and more is the stirred mill. You've got vertical stirred mills such as this, which use attrition to grind the ore. You've got horizontal mills such as the Mount Isa mill, which use horizontal mills, but they use attrition to gently grind the ore. And you can grind very, very fine indeed using stirred mills. Now, the high pressure grinding mills tend to be used for coarse grinding, really replacing things like rod mills, maybe tertiary cone crushers. So for coarse grinding, whereas the vertical stir mill and the horizontal stir mill are used for very, very fine grinding. But recent research is closing the gap, and stirred mills are now being used to grind coarser ore. High pressure grinding rolls are being used to grind finer ore. So the two are coming together. So maybe the future, and not too distant future, is going to look something like this. And sorry about the quality of this slide. The future might be coarse ore going into secondary crushing, then into high pressure grinding rolls, then into secondary high pressure grinding rolls, and then into something like the isomill, which is a stir mill. No tumbling mills whatsoever. I'll say this now, the rod mill is obsolete. Nobody uses rod mills anymore. Ball mills are becoming obsolete. So it won't be very, very long before there are no tumbling mills, except for semi-autogenous grinding mills, SAG mills, because they're very, very big, and they can be used where you've got very, very big throughputs of ore. But maybe in 20, 30, 40 years' time, the SAG mills will also disappear, and you may have something like this. The other big development has been the development of electronic sorting. Now this is strange, isn't it? Because I said that in the 19th century, the only method you had to concentrate ores was gravity concentration or hand sorting. Well, sorting disappeared because you couldn't hand sort fine particles. Now sorting is becoming a very important method again by using computers. You can now electronically sort ores by using colour, by using grade, by using various things. And the place where electronic sorting, it's always been used for diamonds, by the way, the last 20, 30 years, but it's now being used in comminution circuits because you can scalp out coarse rock using electronic sorting. And if you can scalp out coarse rock, then it reduces the load going to the grinding circuit. The grinding circuit is the most intensive energy part of mineral processing. Also, it reduces water because this is a completely dry process. And the two main things which need researching are energy consumption. Energy needs to be reduced. Water consumption. Water needs to be reduced. And this is one of the ways you can reduce water. So you'll see much more of electronic sorting as we go into the future. Sorry about this. Right, the future of mineral processing. I shouldn't be talking about this. You should be talking about this because you're all researchers. So you should know where the future is going. The future is going where you're taking it. So whatever you do is going to be the future of mineral processing. So my ideas are probably going to be quite naive compared with yours and very basic. Where do I see the future of mineral processing? Is it going to be the same as it's always been? You know, you treat primary ores by flotation, you produce a concentrate, you produce copper, you produce lead, you produce zinc by the traditional methods, or is there going to be something else? What's going to drive mineral processing in the future? Well, the electric car. This is basically the second industrial revolution. The internal combustion engine is going. Electric cars are taking their place. I've been very impressed in Changsha seeing all the scooters going around which are electric. Virtually all the scooters are electric. I haven't seen a single electric scooter in UK. Yeah, they're a bit dangerous, aren't they? Because you can't hear them. But Changsha is full of electric scooters. So the electric revolution is taking place. So how will it affect mineral processing? There'll be an incredibly new demand, big demand for certain metals. There'll be a big demand for copper, because copper is used for the wiring. An electric car, typical electric car, takes about 160 kilograms of copper. So you can imagine when all the cars are electric, how much copper you'll need. Luckily, copper is one of the only metals which we can recycle, so that's important. But there'll be a terrifically new demand for copper. There'll be a demand for nickel because these are used in the batteries. And most of the nickel which is now produced is produced from primary deposits, from sulfide deposits. So we need to look at laterites. Much more difficult. There's a lot of laterites around, but they're much more difficult to treat. So we need to look for laterites. So pen that down. That's something you should be thinking about. Cobalt, there'll be a demand for cobalt, but there might be new materials to treat cobalt. I think Professor Sun was talking the other day about using minerals instead of metals in batteries. Batteries will change, you know. But at the moment, the materials we use for batteries are nickel, copper, cobalt, manganese, graphite and so on. And one very, very important metal, lithium. Lithium, very important indeed. So I know you're doing a lot of research at CSU on lithium processing, whether it be hard rock, spodumene deposits or lithium brines. This is the future. We must get more lithium. There's probably enough lithium to go around in the world at the moment, but it's a finite resource. And everyone, politicians and so on, don't realise when they're talking about electric cars and so on, that all the metals which are going to be used are finite resources. They have to be mined. They have to come from the ground. You don't go into a supermarket and say, ooh, I'll have two tons of copper please, and put it in your basket and walk out. You've got to mine it. And that's very, very important. So the electric vehicle will have a very, very big bearing on what takes place in mineral processing in the future. Mineral processing will be at the forefront of this, because you have to think of now new ways of producing metals. The other way is to think out of the box completely. It's not just primary metals, secondary deposits. What about all the tailings deposits which are around the world, which couldn't be treated? Now they can, because you people are developing new methods. As you develop new methods, innovative methods to treat tailings, then the tailings will be. This is the circular economy, where nothing is lost, everything is used. Okay? So that's important. Now what about this? The really big challenge that mineral processing has is recycling. And you talk to people who are not in our industry and you say, we're going to run out of things like zinc and, well, you name it, anything. And they'll say, well, just recycle it. It's not easy. You look at a mobile phone, there are now roughly the same number of mobile phones in existence as there are people on the planet. It's about 7 million. It's huge. It's hard to believe, but it's true, you know. Because when you take a phone in to recycle, you've still got the old phone. And what do they do with the old phone? I don't know what they do in China, but when I take my phone in to a shop in Britain, because I'm due for an upgrade, which I don't really want, but I take it in anyway. I've only had my phone 2 years. They say you can have an upgrade. So I take it in, and they say, leave the old phone, we'll recycle it. Well, they don't. All they do is crush it and put it into landfill. So it's not recycled. Why is it not recycled? Because it's so difficult. Roughly 50% of all the elements which are in the periodic table are present in a smartphone. But it's present in tiny, tiny quantities. So it's very, very difficult to separate them. Now, I know you're doing quite a lot of work on this, and I think it's very, very important that we start to look at how we recycle material which is in old computers, smartphones, etc. Incredibly important, but incredibly difficult. It's definitely the biggest challenge which faces us. I'll give you one example. You look at the touch screen. All these things have got touch screens. Your phone's got a touch screen. Everything's got a touch screen. And the most important metal in a touch screen is indium. Now, 20 years ago, nobody had heard of indium. You know, it's just a metal. Nobody had heard of it. But now you can't have a touch screen without indium. But in a mobile phone, only roughly 0.02 grams of indium are used in a mobile phone. Tiny, tiny amount. Try to recycle that. Try to recycle it because it's also alloyed with tin and oxygen. It's an oxide. So how do you recycle it? Well, that's a challenge for you. You must look at it. How do you do it? Because although it's only 0.02 grams, there are so many mobile phones in existence that the demand for indium worldwide in a year is about 600 tons. May not sound a lot. That's all you need, 600 tons per year. But the actual reserves of indium are estimated to be only about 14,000 tons. So in just over 10 years' time, there'll be no indium left, unless you find a new way of recycling it, or you find a new way of producing a touchscreen. So these are the challenges which lie ahead. They're very, very big. And I think this is probably one of the biggest. How do you recycle material in waste, electronic and electrical equipment? Very difficult. Just want to say finally, I wish I was 40 years, 50 years younger and coming into mineral processing now, because you've got tremendous opportunities. So basically, be proud of being mineral processors. What you're doing is basically saving the planet, saving civilization, saving society. It's very, very important indeed. Okay, thank you. Okay. I doubt whether there'll be questions, but if anyone wants to ask a question. Oh, yeah, yeah.
What type of element we have used in touch screen?
Sorry?
What type of element is available in the touch screen when we use the touch screen?
Indium, tin.
And where is
The material built into a touchscreen. Basically, an alloy of indium and tin and oxygen.
So cannot be recovered by?
Well, I suppose it's possible to recover the alloy and use it again. I don't know. But if you actually want to recover the indium, that's very, very difficult. Yeah. But a lot of people are trying. I mean, you can do it. You know, it's quite easy to do. But do it economically when you've only got 0.02 grams there. That's the problem. Yeah.
Just indium or alloys, a lot of minerals together to make this.
Sorry?
My question. We use just indium mineral.
Indium.
Indium
Yeah.
mineral to make.
Well, it's not an indium. It's not. Yeah, it's not an indium mineral. It's not an indium mineral. It's a byproduct of zinc processing. So you need zinc mines to produce indium.
Byproduct from.
Yeah, there are no indium mines.
Okay.
So they're I think that's the same with germanium, isn't it? Gallium. They're all byproducts of base metal mining. So you need base metal mining to produce these other things.
From tearing of zinc product.
Not recycling. No, when you produce a zinc concentrate.
Byproduct of zinc industry.
Maybe zinc, mainly zinc. When you produce the concentrate, so it's got to be mined and concentrated to produce your zinc. Within that, when it's electrolyzed, you'll produce indium as well. Yeah.
Professor,
Good.
very well. Thank you very much for your wonderful report. I would like to ask you a question. What kind of relationship do you think between mineral processing and metallurgy? And what can we learn from mineral processing to help the development of the downstream metallurgical industry?
Go on, what was that? Could you?
What kind of relationship between mineral processing and metallurgy?
You're talking about things like hydrometallurgy.
Mineral processing.
Yeah.
And
When basically when I'm talking about mineral processing here, when I talk way back about flotation, that was physical separation. When we talk about things like this, mineral processing encompasses everything: hydrometallurgy, biohydrometallurgy. They'll all be used, integrated into trying to recycle these materials. So there's a borderline. Obviously, you're either a hydrometallurgist or a mineral processor. But if you're trying to concentrate these things, you use mineral processing, then it goes to the hydrometallurgist. So hydrometallurgy is going to have a very, very big part to play in future. Most of the developments actually in the 20th century were hydrometallurgy rather than mineral processing as such. You know, solvent extraction came in the 70s for copper initially, ion exchange, biohydrometallurgy. They all came in later. But we've all got to work together. And I think it's very important that if you're a mineral processor, if you're a comminution expert, you also need to know about flotation. I find it very difficult these days that people are so specialised that if they're involved with flotation, they don't know anything about comminution. And if you're working on a mine, if you've got problems with flotation, in most cases it's a comminution circuit, not the flotation plant. So be aware of everything.
大家还有问题吗 ？Okay.
Okay.
Thank you. Thank you for your wonderful presentation. OK， 大家再鼓掌。明天的同样的时间还有一场报告，就是大家都知道 Mineral Engineering 这个期刊在我们领域里还是比较重要的，就是说它会告诉大家怎么去发表，就是说怎么更容易在 Mineral Engineering 发表论文，因为这个中国投稿量很大，但是我们的拒稿率也很高。这个 Mineral Engineering 现在拒稿率可能接近80%，但是我们中国人投过去的稿件拒稿率接近90%，有很多原因，有的是语言的问题，有的是研究的这个 topic 这主题的问题，还有其他的一些原因。就是明天威尔斯会跟大家分享一下，怎么更容易在这个 Mineral Engineering 发表论文，请大家按时2点半过来，好吧？谢谢大家，今天就这个啊。
The USB, or the USB is that?
USB?
Yeah. Is that mine?
Yeah.
Ah, it's funny, it's got China on it. Yeah, it is mine. It's got China. Got the in
Made in China.
Yeah,
Maybe
made in China.
Made in China.
Yeah. I think they probably all are. Yeah. Is that okay?
Yes.
Oh yeah, yeah. I'll get a picture of.
Okay.
You've only got two researchers who are outside China, haven't you?
Two researchers.
This guy and.
The guy.
Yeah. So
Mohammed.
can you? Is he got? Oh, he's there. Yeah. I want to get a picture of us.
Okay.
We'll do that with that background. Yeah.
Yes. The